Okay, so the next other thing we have to talk about is binomial distributions. Now, binomial distributions are really very common in kind of real life applications, because for something to be binomial, it just means there has to be two possible options that we're looking at. Okay, so for example, spinning tossing a coin and getting heads or not heads, spinning the spinner and getting white or not white. That would be two things, okay? Playing a sorry, my TV just turned on. Playing a game and winning or not winning. All right. So anything where you've got two possible options is what we call a binomial distribution. All right. The second thing is, for something to be a binomial distribution, the probability of something occurring cannot really change throughout the probability. So the number of times you do an event, the probability is consistent through all of those different events. Okay, so if, for example, we're looking at, in fact, I want to just, you guys don't need to write this down, but we're going to look at tossing a coin first, okay? So when we're tossing a coin, okay, if we toss one coin, we have two possible things that can occur, okay? We can either get a head or we can get not a head, okay? The probability of that occurring is a half, okay? Probability of that occurring is a half. Right? So we got one thing that can happen. If we toss two coins, and we now change the things that can happen, we can either get heads twice, okay, which we'll do the probabilities after, okay. We can get heads and tails and heads, or tails and tails. Oh, sorry, I was using heads and not heads, wasn't I? Okay, so we should just change. I'm sorry, I'll just change that quickly. Okay, so heads and not heads. Not heads and heads, and not heads, not heads. Okay, so we've got four possible options, so that's going to be a 1 out of 4 probability. Now these two are really the same outcome, just in different orders. Okay, so we've got a 2 out of 4 or a 1/2 outcome of that occurring. Okay, and the last one we've got a 1 out of 4 again, okay, a quarter. So in this we've got a 1 and a 2 and a 1 chance of that occurring. Right? If we now look at 3 coins, okay, we can either get 3 heads, 2 heads and a tail, 1 head, 1 tail, 1 head, a tail, a head, and a head. We can get a head and 2 tails. Okay, so I've gone into the tails, not heads, but that doesn't matter. Okay, we can get a tail, a head, and a tail, a tail, and a head, or we can get 3 tails. Okay, they're all the things that can occur. So altogether, we have 8 possible things, right? Our probability of getting 3 heads is 1 out of 8. Right? Our probability of getting 2 heads and 1 tail is 3 out of 8. Probability of getting 2 tails and 1 head is also 3 out of 8. And our probability of getting 3 tails is 1 out of 8 as well. So we have a 1, a 3, and a 1 probability. Now, if these numbers are looking familiar, they should, because they relate to Pascal's triangle. So again, binomial distribution, binomial probabilities, they should all kind of be coming in and should be remembering them nicely. Okay, so for our coins, okay, we have 1 1, 1 2 1, 1 3 3 1, 1. If we're tossing 4 coins, our probabilities would be like this. If we were tossing 5, we would have these combinations. Okay, now the probabilities relate to that because we can the probabilities relate to that because if we, for example, take this probability of tossing 3 coins row of our Pascal's triangle. Now if we look at the outcome where we've got 2, so we'll say this is getting 2 heads and 1 tail. Okay, we can work out the probability for that. So that's 2 heads, 1 tail, okay, by saying that's going to be 3, which is the coefficient that we get from Pascal's triangle, times by the probability of getting a head, which is half, squared, because there's 2 of those, times by the probability of getting tails, which is another half. Now if we work that out, we get 3 times by a quarter times by a half, okay, and all together we get 3 times 1 over 8, which is 3 over 8, and that is the same probability that we see there. Okay, I'm just going to pause this and delete this quickly, and we'll come back to that example that's above there. If you want to write this down, you can, maybe on the back page of your notes, but don't feel like you have to as well. All right, just hold on 1 second. Okay, so we want to find the probability distribution of the random variable x, which represents the number of times out of 5 that the spinner shows black. If it lands on black, that's a success. If it lands on white, that's a failure. Okay, so we're going to draw up our probability distribution table. I'm just going to, sorry, just turn my pen on. I'm just going to draw it up here. So we've got x, 1, 2, 3, 4, 5. There are our possible outcomes. Okay, and we have the probability where x equals x. Sorry, I'm running out of room. Alrighty, so if we're now going to work out the probabilities of these occurring, we can use our binomial distribution. So I'm just going to draw up Pascal's triangle, really little here. Obviously, if we're looking at 5 trials, we're going to go up to the 5th row. There it is. Okay, we're going to be using these as our coefficients. Okay, so we're going to look at the probability where x equals 1. Right? That probability where x equals 1, that's where you would be landing on, oh, sorry, I've actually done something wrong. Hang on, I just need to change the values in my table and add in 1. Rookie error by me. We should have, because we obviously have an option where we have 0, and I was explaining to the others in class yesterday, again, that you always, like in Pascal's triangle, like when you're doing your binomial expansion, you always have one option where you've got 0, okay, so you need to remember that, not forget it like I did just then. Okay, so if our probability where x equals 0, that's where we're not landing on white at all, that's where we're not landing on black at all. So our coefficient is 1, so we've got 1 times by, now the probability of success is 2/3, and we're looking at that happening 5 times, okay? So if I go to my calculator, I can do 1 times by, now obviously you don't have to do the 1, but there you go. Okay, 1 times by 2/3, okay, to the power of 5. All right, and we get 32 out of 243. Okay, so 32 out of 243. So that's my probability. Okay. We can now, obviously, the probability of it being 5 is going to be the same as that. So probability where x equals 5 is going to be still going to be 1 times by, but now the probability is going to be of success, not of failure. So it's going to be where we've got 1/3 to the power of 5. Okay, so to go back here, I'm just going to edit this to make that 1/3, enter, we get 1 out of 243. Okay, so 1 out of 243 for the third one. Okay, the next one's going to be the probability where x equals 1. So that's going to be 5 times by 2/3 to the power of 4, because we're expecting that to happen 4 times, and 1/3 to the power of 1, because we're expecting that to happen once. What I'm going to do is I'm just going to pause this. I want you to fill out the rest of the table, and then you can check your answers when you're done. Okay, bye. Okay, so hopefully what you should end up with is 32 out of 243, 80 out of 243, another lot of 80 out of 243, 40 out of 243, 10, and then 1. And again, same thing as what we were saying before, all these probabilities should add up to 1. So if you've done it correctly and they all add up to 1, then you're probably on the right track, okay? So you've got 80 is 160, 40, 200, 10, 32, that's 242, 243 if you add on the 1, okay? And you see here, this is a tiny probability that you've got to spin this 5 times. It's going to land on black every single time, okay? All right, we'll go on to the next one. This is just a formula saying the same thing that I said before. So this is the sum of all your probabilities. So that's your combination, that's your Pascal's triangle bit, times by the probability of success, times by the probability of failure, equals altogether equals to 1. Okay, I wouldn't worry too much about this particular notation. It's just to show you, to kind of relate this to binomial expansion. Okay, so things are only a binomial distribution if there's exactly two possible outcomes. I already said that at the start, success and failure, okay? And they have to be mutually exclusive. So remembering that's when you've got your Venn diagram and the two things do not overlap, okay? Obviously, if they overlap, that would kind of create a third condition, so that should be fairly obvious. The outcome of each trial is independent, so that means the probability is consistent throughout all of your trials. And the probability of success, that's exactly what I just said, so that's fine. And then the other thing is that you need to have a fixed number of trials, n, that take place, okay? So this doesn't work if you say you have infinite or an undefined number of trials. You can only calculate the probability if you are aware of what that n value is. Okay, the random variable x, which represents the number of successes in the trials in this experiment, has a probability distribution given by, now again, this is just expanding on that Pascal's triangle theorem. So you've got, this is your n choosing r. So remember, that's your NCR button on your calculator. That's what you can use to find the combinations. Okay, so it's your number of combinations times by the probability of success times by the probability of failure. So for example, that 1 minus p, if your probability of success is 1/4, that 1 minus p, that just tells you your probability of failure or not success would be 1 minus 1/4, okay, which is 3/4, for example. All right, and that's to the power of the opposite number, so your not successes. Okay. All right, so we're going to state whether a binomial distribution could be used in each of the following scenarios. So a fair cubical dice is rolled 10 times, so we've got defined times, we've got defined outcomes because it's a dice, so it's random. Probability of getting 3 4s, 4 5s, and 3 6s. Yes, we could absolutely use a binomial distribution for that. A fair coin is spun until a head occurs. Find the probability that 8 spins are necessary, including the one on which the head occurs. Again, yes, we have a defined quantity of things that are occurring. Coins are random, the probability remains consistent, so that's fine. A jar contains 49 balls labelled 1 to 9. 6 of the balls are selected at random without replacement. Find the probability that 4 of the 6 have an even score. Okay, so balls labelled 1 to 49. Your probability that it would be 6 of the balls are selected at random. So you're taking out 6 without replacement. Now this is the tricky bit, because this would not be a binomial distribution because each of your probabilities would change after you've selected the ball. So once you've taken 1 out, your probability is then you've only got 49 balls left and the number of evens and odds are going to change. So that would not be a binomial distribution. Okay. Jar contains 49 balls labelled 1 to 9. 6 of the balls are selected at random with replacement. Find the probability that 4 of the 6 can have an even score. This would be binomial because you've got that replacement, so the probabilities are remaining the same. Okay, all right, from this, I think you can go and have a look at exercise 6b. I'd like to strongly encourage you to do some of these questions, and I'll be back on Thursday with some more information for you. Okay, I hope you're having fun at home. We're missing you all in class. Okay, bye.